So good afternoon, everybody. It's 4 p.m., so it's time to start our new event, online event. This time is a Epic members new product release. It's an opportunity to our members to show us the new developments, the new products, and understand what's happening in the industry. And we have, as you can see in my slide, a set of companies that will introduce the last developments and solutions for different applications. Just before starting, a few words about EPIC. This is the European Photonics Industry Consortium, an association of more than 800 companies related with photonics somehow. Can be manufacturers, can be system integrators, users, components, manufacturers, service providers as well. And the idea of the community is to work together to ensure the sustainability of the photonics business in Europe, and also to help the different members from our side to find new partners and new collaborations. This is a short summary about the EPIC staff that we are, as I mentioned, working with our members to help them with different market reports in order to will show what's going to happen in different industries in the future with different technologies as well. We can help with the technological request in case they are looking for alternative suppliers or for different companies that could help them in the development of a solution. We help with investment needs and also human resources, and also with the networking. That is one very important part, and that's one of the reasons of a lot of our online and on-site meetings as well, to bring a community of people interested in the same topic in the same place as well, so they can discuss and find, as I mentioned, new partners and new collaborations. In this sense, we have a lot of EPIC events, so I encourage everybody attending today the meeting to check our website. Regarding the physical meetings, we will be back in September with few technological meetings. The first one is going to be about new space applications during the ESA Industry Days. And we will talk about also photonics for miniature size optics at Sony DADC and the laser microprocessing and light conversion. Of course, we will be present at ECOC conference. So if you are attending and you want to join one of our events, like the VIP networking session or the career booth, just check our website to know more details about what's going to happen there. And of course, the delegation to Taiwan, that is an activity that we do only and exclusive for EPIC members, where we bring companies to different countries around the world, so they can establish new partnerships, new collaborations, find customers. It's a very interesting thing. So if you want to explore the possibilities of your company in different countries, just contact us and we can explain you more in detail what is in mind for the future. We combine, of course, this physical meeting with online events. So we will have, of course, technological meeting, but also market reports on perovskite in this case in July. Also, we work in sustainability work groups, and we will have a special online session about membership benefits. So if you are not a member and you like to understand more what can EPIC do for you, you can join us of September the 9th in this online meeting where our director, Carlos Lee, will explain all the benefits and all the activities that are organized within EPIC. And that's everything from my side, because we have a set of nice presentations today, so I don't want to waste much of your time with general information. We will try presentations from TeraXion, PowerPhotonic, HORIBA, Coherent, RP Photonics, and also Lisa Cheval, a member of the LACIA group. So it's a pleasure for me to talk about a lot of different technologies, several related with laser, processing of materials as well, semiconductor lasers as well, metrology-related components. So we are going to learn what's new in all these companies. So I would like to introduce our next speaker. So it's Mr. Patrice Dionne. He's product line manager at the company TeraXion, and he's going to present the LXM, a new generation of narrow linewidth semiconductor lasers. So Patrice, the floor is yours.
Thanks, Antonio. You hear me well?
We hear you well, yes. You can share your screen.
All right. So you see my screen now?
Yeah, everything good.
Okay, so thanks again, Antonio. My name is Patrice Dionne. I'm the product line manager for optical sensing and TeraXion, and today we're introducing our new narrow linewidth laser module. So About the company, TeraXion, we're in the business of photonic components since year 2000. First developing components for optical communication markets. Since then, we diversified a little bit and have a component offering for different markets and application. In terms of technology expertise, most of our components are made of fiber Barrie grating, high specialty fiber Barrie grating, for example, dispersion compensator, pulse stretcher, ultra narrow bandwidth filter. And we also have a low noise laser product line since year 2005, actually. We've always differentiated ourselves through the quality of our control electronics. And since few years, we start developing our own chip. And this is what's new with our laser product offering. And that's the topic of today's product introduction. So if we talk about the LXM, what is this product and how does it bring value? So it's a laser module based on a DFB monolithic semiconductor chip. TeraXion now manage the process from wafer to chip to packaging into sealed and temperature controlled butterfly. So we're fabless. We're working with a Canadian fab company, and the LXM is really a module offering. So it's a turnkey module with low noise drive electronics. I've mentioned the chip. It's a chip we worked hard on the design that displays key differentiators at the performance level. So we, as I said, we manage the process to chip on carrier, packaging into the butterfly, and we add on top of this tech controller, low noise current source, frequency modulation circuit to offer a turnkey module offering. There are two flavors, and by the way, I forgot to mention here, but the wafer we designed so far are in the vicinity of 1550 nanometers. So this is the wavelength we're working with today. I've mentioned two flavors, either a DFB laser under direct drive. It's what we call the LXM-S for standard offering. And we also have an ultra narrow line width version where the DFB is frequency locked on a frequency discriminator. This is the LXM-U for ultra narrow line width. The locking circuit, frequency locking circuit, it's built in the electronic. Same for the frequency discriminator, it's built in the butterfly package. And in terms of difference, main performance difference between those two models, the direct drive is the intrinsic line width of the DFB chip below 25 kilohertz. With the frequency noise cancellation circuit, we achieve ultra narrow line width. And for the LXM-S, it's the modulation circuit is directly connected to the laser electrode. What's limit the modulation amplitude is simply the protection circuit of the modulation circuit. The LXM-U, considering the laser is slaved on the discriminator, we do not have the same degree of freedom, and that's why the modulation amplitude, when we want to frequency modulate the chip, is limited to 200 megahertz. Now, if we look at the technology differentiators at the DFB chip level, it's an intrinsically narrow chip. This graph, we show DFB from supplier packaged with our low noise electronics compared to our own DFB, and where we see there's we worked hard on designing a chip that was intrinsically narrow. And the second differentiator at the chip level is that we developed a chip with a flat frequency modulation response that was mandatory for some of the project we have internally with frequency locking and phase locking loop. So it allows high performance frequency locking and phase locking of the laser. And it's also a fundamental to maintain frequency modulation properties at fast repetition rate, which is a added value of the LXM-S module. And now if we look at the product differentiator at the module level for the LXM-U, what stands out is really the ultra narrow line width, which is better than high-end fiber laser between 100 Hertz and 100 kilohertz. So here is the power spectral density of frequency noise. The LXMU is in green. In terms of a rugged and reliable laser that have been designed for industrial application, this low level of frequency noise is pretty unique on the market, and it can give enhanced sensitivity as well in range to sense a phenomena that has this signature in those frequencies. Now, if we look at the LXMS, what's unique with this module is the combination of fast frequency modulation properties combined to the intrinsic narrow line width. So even if we want to modulate it fast as it's used in FMCW LiDAR, let's say 100 kilohertz repetition rate, we can still achieve a high modulation amplitude. The chips react well at high repetition rate. And last slide, and important to mention, those are rugged and reliable laser delivered on spec. We've been in the business of low noise laser for more than 18 years. We have a history of stability, reliability, and ruggedness. We also deliver low noise lasers on spec with a high level of support. And what's new now with our own chip is that the LXM brings key performance differentiators. So you have my contact info here. Please send us an email, give us a call. I think our laser can bring value to your system. Thanks a lot.
Thank you very much, Patrice. So we have time for questions. So do not hesitate to raise your hands and also use the chat or the Q&A boxes to make your question to Patrice. I will perhaps start with a question about applications. You mentioned LiDAR a little bit, and sometimes really this line width can be interesting for applications, but you can perhaps mention a few more cases in where your laser could be very interesting.
Ultra narrow line width is important for distributed acoustic sensing application. So long range fiber sensing based on relay scattering will benefit from a low level of phase noise. So FMCW LiDAR is an example. Also, fiber sensing, distributed fiber sensing based on frequency modulation. The laser can behave well for this. So having two flavors, one that is focused for ultra narrow line width, maybe less modulation amplitude for longer range, lower spatial resolution. It's a good fit. And the standard version for maybe medium range but high spatial resolution can also be a good fit for those applications. Those lasers are also ultra stable, so they're used for quantum communication as well. Advanced metrology, this kind of stuff.
Very good. In the case of the distributed acoustic sensing, is something that could be used by the company to develop the fiber sensor itself, or perhaps more than a user that could perhaps, or somebody doing a service with this kind of solution that want to improve the capabilities of their system?
No, I think it needs to be integrated by the system developer themselves. So it's really at the design stage of new generation of interrogator. Yeah.
Very good. I don't know if there is any other question for Patrice. Well, if not, thank you very much for the great presentation.
Thank you.
And we encourage everybody to contact TeraXion and Patrice to discuss your needs more in detail. Also, you can contact us back if you want to be introduced, so you can discuss further your need and your application. And we can move to our next speaker. So it's Scott Barrie from the company PowerPhotonic. He's going to present the coherent beam combining module. So Scott, the floor is yours.
Thanks, Antonio, and thank you very much for letting me to be here and present. So afternoon to everybody. I have got some information just to introduce you, if you've not heard of the company before, about what we do and an overview of some of our more modular products that we're moving towards producing. So I'll share my screen and pick the right one. I mean, there's only two, so it's 50-50. I'll go for it. So if you haven't heard of us before, PowerPhotonic, we are a manufacturer of optics, freeform optics, based in the UK, just outside Edinburgh. So I always say Edinburgh because nowhere really outside Scotland knows where this place is. So we are, if you know where Edinburgh is, we're about 30 minutes drive outside there. And we're a relatively young company, so we started shipping products about 2006. And over the years, we've had a number of different applicational focuses. Previously in the past, there was a lot of interest, a lot of business done in telecoms markets, stuff like OCT and cinema projection. But towards over the last sort of 5-6 years, there's been a heavy focus on defense applications, and particularly high power applications, and also industrial and commercial markets. So I so much interest that we opened up a site in Arizona, just outside Tucson, which seems a place to be for factories at the moment in Arizona, which is largely based on the amount of business that we have in the US, and having manufacturing sites there was a much bigger advantage. We opened that over the last sort of 18 months. The total company is about 50 people, and that's about 95% in the UK. But the US team is now in the process of hiring optical engineers, and then they have a similar size facility over there as well. So it's really exciting for the next kind of couple of years, and the ideas will be a similar size over the next kind of couple of years in the US. So I'm just to sort of give you an overview of what we do. I'm not going to go through this whole slide, but we have a unique direct writing process of how we make our optics. So it's a laser writing process, and it sort of goes in two passes. So I say that we use the laser to create our structures on the glass, and then we polish the glass and create like a really ultra smooth, low scatter surface. So this lends itself very well for these high power applications because we maintain a very high LIDT in the bulk material, and we have as I mentioned, it lends itself very well for these high power applications. So we do a lot of applications like material processing and defense applications like CDC, which I'm going to touch on. So I've worked in this industry for about 7-8 years, and I've done some various different markets over that course. So I'm aware there's different jargon. Sometimes people are aware of certain jargon, and other people maybe use the same term or different terms for the same thing. So just as an overview, when we're talking about power and bucket, which is a key parameter for CBC systems, power and bucket effectively means how much power you have in the center of your beam. What's unique about PowerPhotonic is that we offer a hexagonally tile corrected CBC process where it increases the overall theoretical limit of power and bucket that you can achieve. And this is much higher than if you have a look at sort of current research papers that are concerning CBC, where a lot of them are looking at Gaussian systems, or i.e. no beam shaping. The theoretical limit is about 66%. And by using our sort of solution, we can increase that. So that's the benefit that we want to sort of provide to the people we're speaking to. So the benefits of this, what does that mean in actual real world terms? So the advantages of this would be obviously if you have a higher power, you can use these terms like defeat time. In defense, there's some questionable terminology, I would say sometimes, but faster neutralizing time, if you wish, or a lot further distance, higher propagation. Or if you inverse that, which is particularly important to certain people, obviously it's running costs. A lot of these a lot of the companies that we speak to are in defense sort of environments where maybe things like running costs aren't necessarily a concern at this time with sort of developments. They will be in the future as this TRL demand raises, but we also have, which I can touch on at the end, we've had some interest for the system in other applications. So originally we intended this for a very specific application in defense, but since we've released a white paper on the product and we've been doing some promotional activities, we've got a lot of interest in a lot of other different applications that we didn't think of to begin with. So things in like material processing, things in fusion. So it's a really interesting product, and that was particularly why I wanted to sort of take time to do this presentation today and to see if we spark some ideas from anyone. But in general, in commercial applications or in any application, these are the main things that concern about: reducing the power, reducing the running costs, reducing the cooling requirements, particularly for systems of these energy power levels. We're talking about in some aspects, the systems we're looking at is in like hundreds of kilowatts range, which and to touch on when I talked about Gaussian systems, one way to sort of, without beam shaping, one way to increase your power in bucket is to effectively turn up the power or overfill your channels, which is a good workaround, an easy workaround. But when we're talking about power levels of this magnitude, even 1% over, you're talking about 100 kilowatts, is still a pretty significant loss. And will again increase your cooling requirements, etc., etc. So these things are, as I said, still in development, and these things are talking about deployment times of like in the 2030s, although they seem to be getting more advanced now. These will obviously be considerations now, but will become greater considerations in the future. At the moment, it's more about proving the system in theory, and then moving towards sort of lower swap, which is what gets referred to a lot of time with these defensive applications, is low size, weight, and power. So just to touch on what we've done, so since 2002, we've optimized the optics that we make for these different channel systems. And in theory, you can increase this to an infinity, but obviously there's, in real world, there's certain considerations. I don't know. It's a terrifying prospect to think about a laser weapon that's in infinite channels, but in theory, this can be scaled up. And then the tiling is just largely based on the numbers is largely based on the tiling or the packing that you get from a hexagonal pattern. We've built and tested a 7-channel system, and we've done simulations for the larger channel systems. And then the point we're at the company now is that we want to have more, or get it in front of people and have it tested in sort of in situ environments. So as a sort of overview, because I touched on a few things there, but what was it we provide with this increase in PID? If you look at the sort of recent research papers, the sort of 60%, 70% is the sort of level that they're at now. There are others that are sort of similar or pushing towards 80, but we've got a pretty good solution versus the market, and it's and it clearly has a benefit over a Gaussian system. You don't need to overfill your channels, therefore you don't have to increase your power consumption. It's a monolithic solution, so we can reduce the size, weight, and power of the device. And having a monolithic solution makes more ruggedized for the types of environments it would be in. And as a salesperson, I'm always saying to people, we need to make it as easy as possible for our customers to test our solutions, i.e. put them in modules, put them in assemblies. Sometimes quite difficult to, if we go to, I mean, some engineers are quite happy to do this sort of thing because they're interested, it's a novel application, so they're happy to sort of figure out how to get this into their system. But something that's essentially you plug in your fibers into the back of this and you'll have one coherent beam output from that. There's other elements to it with like IE phase control, but in theory, that is much more easy to work into a system than this. So that is the sort of, as I mentioned before, we've made discrete optics. But what we're moving towards now, especially in defense application for CBC, is more modularized solutions. And And just to sort of summarize, and I touched upon it before, but the intended application of this was for very specific, like a defense application situation. But in effect, you can think of it as an amplifier of sorts for your laser systems, or various laser systems, to get one coherent output. So if you're looking at material processing, we've had a lot of interest for material processing applications, also for LWFA, so laser wake field acceleration, and there's probably others. Like we've also had stuff for optical communications, where we're looking to space communications, where we need higher power or to get over atmospheric disturbances. Not as high power as defense, but there's certainly a lot of other uses for this device, which is really interesting. So if anyone's got any questions, we've got a white paper that's quite comprehensive and has all the information for our test results. There's some other plans that we have that are a bit more confidential, but in terms of our timeline for development over the next 6 to 12 months. But if anyone's interested and you want to have a conversation with me, feel free to drop me an email, ask some questions, and I'm more than happy to give you some more information. So thanks.
Thank you very much, Scott. We have again time for questions. Yeah, Clement from High Labs.
Hi. Thank you, Scott, for the presentation. I was wondering if you have a phase control solution for your array of emitters, and how do you perform it? Do you pick up a leak at the output of your compensating mask, basically?
So the short answer, we don't do active phase control on the solution at the moment. So we were purely focused on the beam shaping elements in the device, so we don't incorporate that at the moment. We are working or speaking to a couple of partners where we're going to do have plans. That is partly what I just sort of touched upon in terms of the plans, but it's a bit more sort of confidential. But we have plans to do this.
Okay. Clement, is your question answered? I think so, because you still have your hand raised.
Yes, sorry.
Okay, thank you very much. Any other question for Scott?
Yeah, I think I've done that before as well. We've talked about the epic question. So I touched on the size what we can provide in terms of increasing power and bucket, which is the key parameter for CBC systems. What we are sort of looking for is we're quite interested. As I said, we don't have a kilowatt laser system in-house, unsurprisingly. So, but we have partners that we work with in the UK and the US. But we're interested in, particularly for, as I mentioned, it's aimed at this defense and CBC applications. But for there's a lot of interest for other stuff, like what I'm quite interested in, a lot of the stuff on fusion, which sort of touches on what I did in my degree for LWFA, and for material processing. So if anyone's got some ideas or seems interested, feel free to get in touch with myself.
Good. Thank you very much, Scott, and thank you for the presentation.
Cheers. Thank you.
And we can move to our next speaker. So it's my pleasure to introduce you, Olivier. He's Director of Innovation at HORIBA in Palazzo area, and he's going to present the camera readable pattern at position scale. So Olivier, the floor is yours.
Okay, many thanks, Antonio, for this introduction. And so I will share my screen and then go to full presentation mode. Here it is. A few words about HORIBA France. Maybe you know HORIBA in France, and also the Job technology brand for diffraction gratings, for spectrometers, and for spectroscopy instruments. Today, I will speak of something different, which is a new product that we are introducing, which is a position and motion sensing solution that we call Nano GPS or OXIO. So it can be of interest to you if you use or integrate positioning or motion systems it can be of interest to you if in what you are selling or in your production facilities, you care about position accuracy or reproducibility or drifts. And another condition that you have a camera, a vision camera or microscope camera in your system.
We hear you quite bad, Olivier. I'm not sure if it's because of this video moving.
Oh, sorry.
Now it's better, yeah.
Okay. And so I should stop the video from moving. And so it is in the context of you have some camera or microscope and any positioning system. And in that case, our position sensing solution, which sell as kits, that includes a scale and software. And with the camera, you take images of the scale. And what it looks like is, when you look at the image, is a field of QR codes. And these QR codes encode the position. And using the software, the image is decoded into position and orientation. So I will again put the film and stop speaking so that you can see what the image moves. The decoded image provides X, Y, and Z. Oops. So it's the one. So let's look at the film. So this is basically the principle of this technology. And what is interesting to know is that it is very precise. It can be precise down to 1 nanometer and 7 microrads, in which nearly nobody is using. It can go up to 300 Hertz with a modern USB camera, so you can see either long drift or also vibration up to more than 100 Hertz. So depending on your vision system you have and the travel you want to check measurements on, the size of the scales can go from few square millimeters to 1 square meter. We have customers that are using different kind of scales. The accuracy depends on the scale, but our most precise scales are quartz scales that provide an accuracy that has been shown to be better than 150 nanometer over 80 millimeter. And of course, we have got different scales that accommodate different working distance. And this technology, we are the only commercial provider of this family of scales. On the right, what you can see is a scale that is, can be used with many vision systems because it has different zones that can be rated with different magnification. And so this is a kind of a slide that can fit different needs, and this is in our evaluation. The reason why we launched this product is that we first integrated this technology in our Raman microscopes, and it was rather successful. So my first message is that if you're producing products that include some motion system and that you are interested to establish the stability and a variety of features related to motion, this can be something of interest, especially in the case your system includes a camera or microscope. Presently, it is used for objective adjustment, meaning when you switch the turret, we have a preliminary calibration that is done with this technology on a very tiny scale. And we just take the image with a different objectives and measure the position, and there is an offset which is attributed to the decentering of the objective, and that we can correct in this way. Our R&D department also adopted the technology for quality control and for qualification. For example, we can detect any moving stages issue. We can detect also any stability issue. And last but not least, software debug, because sometimes we're giving instruction to your displacement tools, but it's not always moving the way you think it is. Production and illustration department also used this for a variety of features, including automated magnification determination and also automating alignment between camera and stage, and automated QC and test, which again can be interesting if you're producing some instrument that you need to be sure of the accuracy, reproducibility, stability, and all this kind of thing. And service department is also beginning to use it to check issues at a customer site, because it is very easy to use this technology at customers. So we put several of the kits, including the scales and the software. Because this is rather new technology, we found that people wanted to play with it before, and it was very helpful for them to figure out how they could use this technology to solve their positioning or drift or reproducibility issues. And our discovery kit allows you to do hands-on nanometrology with less than €1 kilo, and it is available. We have it in stock. Of course, we have larger, more accurate scale. So excuse me. We also have several OEM customers, and I can deal with OEM division manager with some requests. So basically, who is using this type of product? So two stage manufacturers are using it. Integrators of stage manufacturer are using it to build their system. We have also two customers in this field. We have two microscope manufacturers who are using them for either R&D or QC. We have instrumentation companies, and we have laboratories. And more we see robotic solution providers who are using it. We have one OEM customer who is doing micro robotics with 300 millimeter wafers, and so we provide the 300 millimeter scales, and this is helpful to them to have the repositioning accuracy they need. And we have also larger robots in the industry 4.3. With this solutions, you can use any camera for position measurement. And this is important because positioning performance is really a system issue. Of course, you probably have position encoders embedded in your stages and movements and so on. But very often, the stage encoders provide you the position in a referential that is not the one you are interested in. For example, with the stage encoders doesn't tell you about all the drifts that occur within the frame of a microscope or any other instrument. So we provide these machine-readable scales and the software, both for retails and as OEM, we can customize it. And the start to hands-on nanometrology is by getting our discovery kit that is working with any magnification or any vision system. And I will be happy to answer your questions. And we also added a number of peer-reviewed publications that are open access that can also provide additional information to figure out what this new technology can do for you. And I think that's it.
Thank you very much, Olivier. We have time for one question for Olivier. I have one regarding these machine vision applications where nowadays sometimes they are using also spectral cameras, so hyperspectral, multispectral. Did you check your solution in this environment of spectral imaging cameras?
Yeah, well, not so much. We checked our solution in the microassembly, in the field of microassembly, and also in the field of microscope.
Good. So thank you also for the summary of the measures to take home. So everybody that is interested can think if in contacting you to discuss more in detail. So thank you again for the presentation,
Thank
Olivier.
you very much, Antonio.
And well, thank you, Christian. You are fast in the presentation, so it's my pleasure to introduce Christian Lux, Product Line Manager at Coherent. And as you can see in the slides, going to present the Coherent's industry-proven monolithic stack. So Christian, the floor is yours.
Thanks a lot. Can you hear me now?
We can hear you.
Thanks. So thanks, Antonio. Hello, everybody. My name is Christian Lux. I'm Product Line Manager for conduction-cooled bars and diodes at Coherent Mainz in Germany. And I will guide you through the next couple of minutes showing our latest results and products for packaged laser diodes. So to give a brief overview on Coherent, so together with 26,000 colleagues, we generate a yearly revenue of approximately $5.2 billion. Our worldwide located sites are producing materials, components, subsystems, and systems, featuring a vertical integration. So due to such a vertical production, we cover the entire value chain from wafer process to temperature coefficient matched packaging, including optical beam shaping and dense mechanical integration up to turnkey pump engines. Scalability of pump power can be reached by vertical as well as horizontal stacking of diode laser bars. Optical beam shaping allows brightness conservation and maximizes fluence. We offer dense mechanical integration, also leading to turnkey pump engines, of which I will show you some used in recent applications. So how does such a packaging look like? To build a monolithic stack, the unmounted bar material from wafer is soldered into two copper tungsten submounts, which are expansion matched to the aluminum gallium arsenide bar material. So various heatsink designs carry a different number of bars and are available in configurations that serve a variety of applications, either integrated in laser systems or as a direct beam source. These hard-soldered sandwich structures, submount by submount, will be backside soldered onto a ceramic plate, electrically isolating it from the cooling. There are conduction and water-cooled versions. The latter can be used for laser pulses up to a few hundreds of milliseconds, for example, in hair removal applications. However, these of course also support few millisecond pulses at high power for pumping applications and diode pump solid-state lasers. We can attach micro-optics to collimate both the fast axis using a single lens or the slow axis of a lens array. Further optics such as volume Bragg gratings from our fab in Monrovia and even homogenizers from the colleague that just presented can be used to narrow the emitted wavelengths. Also wavelengths narrowing, of course, by the volume Bragg gratings and homogenization by the other optics. So I will now show an example how such diode laser stacks will be used in laser-assisted inertial fusion energy. So we heard about this quite a lot, so it's a quite interesting topic at the moment. And the latest results shown by Lawrence Livermore in December 2022 demonstrate the successful use of lasers for fusion energy achieving ignition. This means that producing more fusion energy than the amount of laser energy delivered to the target. On the left side, such a lamp pump setup is shown. It makes high-intense single laser shop operation available, but only a few shots per day. On the right side, you see a HORIBA target. The lasers focus inside of this target in geometry, supporting such a self-sustaining fusion reaction. So in future, diode pump solid-state lasers will operate at 10 Hz and more and will deliver the needed high-intense laser powers. So back to our laser diodes, we show one of our latest stacks supporting up to 600 watts per bar at the absorbance wavelengths of ytterbium around 939 nanometers. The stack design offers up to 4.8 kilowatt output power. It's fast access collimated and designed in a way to build an infinite assembly. So latest bar material and optimized cooling designs will even offer power values of more than 1 kilowatt per bar. For DP-SSL applications, further active laser dopants of interest are, for instance, neodymium, thulium, and erbium, and the corresponding pump wavelengths are covered by different semiconductor materials that we can also process. For instance, gallium arsenide-based 885 nanometers, 938 nanometers, 790, and indium phosphide-based 1532 nanometers. And what's the next step? The aim is now to maintain the spectral properties of central wavelengths and spectral width in setups of hundreds of these stacks. So shown here is such setup of a 350 kilowatt QCW pump engine optimized to pump cryogenically cooled ytterbium laser media. These pump engines are used for double-side pumping. The very compact footprint allows to place these pump engines into most common tabletop setups of DP-SSL amplifier systems. So each pump engine contains 100 stacks. The short pulse wavelengths of a bar material has been determined for each bar after processing. Binning of bars took place to further narrow the spectral properties of each stack to be built. So wavelength tuning of grouped stacks by operation bias current, cooling temperature, and coolant flow rate enable narrowest line width, even using such a large amount of stacks. So the measured PI curve on the upper right side demonstrates the unmatched high output power of 350 kilowatts due to the excited lifetime of cryogenically cooled ytterbium 3+ pump engines are designed to operate in the range of less than 1 millisecond and at 10 Hz. And on the lower right side, you see a perfect quadratic beam profile of approximately 80 times 80 millimeters. This was achieved using customized homogenizing optics. And all in all, such a 350 kilowatt high power pump engine is perfectly adapted to the application in terms of its temporal, spectral, and spatial profile. I want to highlight two additional markets where such laser diode stacks are used. So here defense. In defense, there are various applications such as direct energy, direct infrared countermeasure, surveillance, target designation, and range finding. And of course, most of these lead laser sources that work reliably even under the prevailing harsh conditions. And here is shown a multi-wavelength stack with 4 bars used for range finding and target designation. So under a wide range of operating temperatures on the field, there's always a bar emitting laser light in resonance with the absorbance of the pumped laser medium, for instance, neodymium YAG at 808. And you see here for the different temperatures. So to achieve this, we sort and select bar material of different cold pulse wavelengths. Third and last market I like to show you is medical aesthetics. So when exposed to intense laser light, melanin absorbs radiation and heats up. This permanently stops hair growth after a few treatments. We show our recent results in bar material for hair removal, delivering up to 300 watts per bar at 55 millisecond pulses. We choose between material of different fill factors, supporting a wide range of pulse length operation, either concentrated at low duty cycle and high power, or at high duty cycle and corresponding lower output powers. Besides the classical 808, different wavelengths are available, such as 760, 940, and 1060 nanometers, somehow related to the individual skin type, of course. And each bar material of these 4 wavelengths show very similar PI curves, facilitating the use in mixed wavelength stacks. Typical 12-bar stack with 200 watts per bar material delivers up to 180 joules. And these stacks can be integrated into encapsulated housings for assembly outside cleanroom areas. In future, a 2-junction configuration will deliver 200 watts of output with just 100 amps of input current, thus doubling the efficiency of previous single-junction bars. So and with this, I'd like to thank you for your attention and looking forward to your questions.
Thank you very much, Christian, for a nice presentation. We have time for questions. Perhaps I will have a question regarding the configuration of the stacks. Is something that is going to be flexible, the number of bars that you're going to include in any stack, depending on the application, or the idea is to have some, let's say, standard amount of bars or standard stacks, and then you will play with the number of the combination of them.
Yeah, usually an industry standard is the width of a bar, the typical 10 millimeter, and then the number of bars that you put in such a stack, this can vary quite a lot. In monolithic setups, it's usually something like 12 or 15 at a maximum, but let's say, and there are different other setups where there is no limit in stacking these bars.
And regarding the fabrication, is always this soldering needed? Could in some cases be the gluing solution, or the energy is too high to...
So soldering is basically needed to contact the bar with a heatsink, but of course then you do not necessarily need to use a sandwich structures. There's also ways to have a direct microchannel cooled heatsink as a cooling. That's the very efficient cooling, but it depends on the way how you use it, how you operate it, and also from cost perspective, there are different aspects to take into account.
Very good. So I understand from the customer point of view, you're looking for integrators in the hair removal, for example, developers of machine for hair removal. In the defense, I guess that companies that can integrate your laser in their systems, right?
Yeah, so mostly OEM customers is the target, yeah.
Okay, very good, very good. So yeah, for everybody in the room, if somebody's interested, please contact Christian to discuss your needs. Thank you very much for great presentation. And we can move to our next speaker. So it's my pleasure to introduce Mr. Rüdiger Paschotta. He's the founder and managing director at RP Photonics, also the developer of the well-known encyclopedia. And he's going to present today the fiber amplifier laser simulations out of the box. So Rüdiger, the floor is yours.
Yeah, thank you very much. Okay, yeah, you know, we are best known for the website, for the marketing opportunities, but even before we started that in 2012, we already had for several years the RP Fiber Power software, and now we have version 8 of that, which is a significant step forward, as I will show you. So first of all, it is useful for simulations, mostly just computer simulations of fiber amplifiers, fiber lasers, but also passive fiber, things like coupling of light between different cores in multi-core fibers, or whatever you can imagine, actually, fiber couplers, all sorts of devices. Generally, simulations are very important because they produce detailed insight into the inner workings of devices, and that they do much more than measurements, and at the same time, without much effort. So you get much more information much more quickly, and that is, of course, very helpful when you do development of such devices like, say, fiber amplifier systems. You better understand the performance limitations and find optimized device designs. You can thoroughly check designs before buying any parts and building a prototype and testing it. And you can find out the cause of unexpected behavior more quickly. And you get inspired for new ideas when playing with a model. Often without a plan, you play with it, you learn something, you find, oh, I can actually use it in this or that way. And the bottom line is you get quality results of your R&D work faster and cheaper. Lab work still stays necessary. You eventually have to realize your prototype and test it, but it will be reduced and will become much more efficient because you're no longer trying things which you could have known won't work in any case. So you improve your designs before trying something in the lab where it becomes cumbersome and expensive. So for that, you need a powerful simulation tool. You need something to produce deep insight. For example, this product calculates fiber modes, simulates power propagation or even full beam propagation in fibers or even outside fibers, actually. You can propagate ultra-short pulses, simulate laser dynamics, etc. All this is done with a nice graphical user interface, which is also highly flexible. And then what is also important, you get high quality comprehensive documentation. You know, powerful software doesn't help much if you don't know exactly what is it doing. And also importantly, we give competent technical support, by the way, going far beyond simply helping with software-specific issues. We also help with all the technology issues related. So it's like included consulting. Now, more about the product. What is new about the product in version 8 is mostly the usability. We found a still better way of combining usability and flexibility, which is generally a challenge, because the traditional trade-off is either you have a form-based user interface, which makes it easy to start working with the software. You just fill in your numbers and start your simulation. But usually that's not sufficiently flexible for real work. And therefore, in the past, we actually started out using a scripting-based approach, which is highly flexible. With that, you can basically program whatever you like, but admittedly, it is substantially harder to learn. And how to bring these together was a very hard thing, but we found a great solution now, so-called PowerForm. So we do start with a form-based user interface, but we managed to get that done with very high flexibility. So, for example, the first point is the forms actually start out providing many, many options and still are quite usable, for example, because we hide parts of a form which are at the moment not relevant. You're not exposed to a lot of detail which is not relevant for you. Second, if you need additional outputs, let's say an additional curve in a diagram or a whole new diagram, you can put in a little script code into the form. That means you do scripting, but only of the very specific thing which the form didn't natively support. And finally, if that is still not enough, because, for example, you need in the form additional input fields for additional parameters on which you perform additional calculations, then we can even extend the form. It's not only we, but even the user can extend the form to make a tailored version with any specific additional things required. And of course, we are happy to help if there are any difficulties with that. And this is how it looks. On the right side, you see the selection area where you select one of the power forms. They cover actually most of the typical application areas like fiber amplifiers working in continuous wave, pulsed, even ultra-short pulses, and various things on passive fibers, for example, for ultra-short pulses when you want to simulate supercontinuum generation also. And then on the left side, you see just the beginning of one of those forms. So you can imagine it's quite easy. You fill in your pulse parameters, some numerical parameters, how many simulation cycles you want, etc. And later on, which you don't see here, the details of your amplifier stages, what fiber, what length of it, etc. And the input data may be stored either in some standard folder when you are not interested where they are, or in your work folder. So that's also flexible options to handle it very nicely. There are further nice, not so new, but still very nice and optimized features, very powerful diagram display windows. For example, you can always switch back to the last version of a diagram. That means if you changed some parameters, did the simulation again, you can always look back. How did it look last time? What changed actually as a result of my change? That's just one example of many for very nice features. We also have very nice interactive windows for interactively exploring beam profiles. That's when you're doing numerical beam propagation, or actually when you work with ultra-short pulses, you can select the position in a fiber and then exactly inspect the pulse which you have at that position. Then documentation is, of course, very important. Hopefully you don't need it too much when working with the forms, but if you need it, it's all there, explained in detail what the model takes into account and what is assumed, etc., which model is suitable for which cases, etc. And as I said, we are happy to help. My colleague Gareth Moore and myself, we are doing the development and the support and help our users very much to get their things done efficiently. Okay, so that was my presentation. I will be happy to answer any questions you may have.
Thank you very much, Rüdiger. Do we have any question for Rüdiger? I can start with one question regarding how the light is introduced into the fiber. Is the tool, can you control this with the tool, or is any way to simulate different ways to introduce the light in the fiber?
Yes, it very much depends on the kind of simulation. You know, in some cases, say you have a fiber laser, you introduce pump lights, so you specify in these forms, actually, you can specify, I think, up to 5 different pump sources with different wavelengths, bandwidth, optical powers, etc. You can switch one off or on very quickly to see how much difference does it make, etc. In amplifiers, you have signals, up to 10 different signals at different wavelengths. If it's a pulse simulation, of course, you have to enter parameters for pulse duration, pulse energy, etc. And then you can inspect the pulses at any position inside the system or outside. Outside you could in principle measure, but often with much more effort. Inside you could not even measure practically, and you learn all this exactly what happens in your device. Often enough, you find some surprises. It doesn't work as you expected. You think something must be wrong until you see, oh, I have overlooked this or that. By just watching exactly what happens in the simulation, you learn so much. And that makes you more competent, more effective, more efficient, and you save a lot of time and money.
And can it be also used by for example, a laser manufacturer, fiber laser manufacturer that want to check if the characteristics of the fiber they are buying match with the reality? So perhaps they have some measurements that doesn't match with the
Yes, sure. I mean, if you simulate what would ideally happen if the fiber really is up to the specs, and then you compare with what you measured, of course, maybe different reasons for any deviations, but deviations, that's not a bad thing. It's an opportunity for learning. That, for example, as you say, your fiber is maybe not as you expected, or that you have some bad splice in the system or whatever, and you can check, could it be this, could it be that? And you much more quickly find out what is wrong and how much can it be improved. Is there still potential for improvement, or is it just what I have is what I can get? And that way you get to the limits much more quickly.
Very good. Very good. So if there is no any other question, thank you very much, Rüdiger, for a nice presentation. And we can move to our last speaker today. So we have Emric Verwaerde. He's the CEO of the company Laser Cheval. He's part of the LASIA group, and he's going to present the new laser machines, the Quartz Geode. I hope I pronounce well. So Emric, the floor is yours.
Thank you, Antonio. Thank you. Yes, my name is Emric Verwaerde, and I am the Laser Cheval CEO. Thank you to give me the opportunity to introduce our new laser machine, the Quartz Geode. First, some words about the LASIA group that we included 2 years ago now. We are present all over the world with 6 plants and some distributors. Laser Cheval is based on the east of France. It means an area well known for its skills in micromechanicals. The range of product that we provide start from optical system for laser and go to a standard range of machine, a large range of machine, and also custom laser machines. About Laser Cheval, we have a range of machine based on 4 different structures, from the LEM2, the smallest one that you can see at the left-hand side, to the Yolite machine, which is the biggest structure. We are working only on infrared laser, so from continuous wave to a femtosecond laser, so continuous laser most for welding application, and femtosecond are used for highest quality machining application. We can add a lot of additional equipment in our machine: mechanical axis, automatic or manual vision, optical option, and so on. Let's go deeper about the Quartz, which is our new machine that we present 2 weeks ago in Geneva. 2 issues drove our development. The first was a technical issue, of course. We are always trying to do smaller and smaller parts, more precise, more quality, of course, with more performance and more productivity. But it's not enough. Today we have also to consider ESG issues. and use less and less raw material, less and less energy, produce less and less weight, and so on. So it's what driven our development, and this reflection gave birth to the third generation of our quartz machine. This machine can accept all of our option. It means that we can put laser from continuous wave or CW or QCW laser for welding application, nanosecond laser, picosecond laser, and also femtosecond laser. We can put up to 5 mechanical axes in the machine. And also we can, more than the scanner head, we can also put a third optical axis to machine or to work on 3D parts. We also propose a large range of focal lengths and up to 3 camera, and of course lighting adapted to what we need. Something new we develop by ourselves, a stacker with 48 pallets. It's a cat stack, 4 stacker of pallets, and we can put 3 different. We can parameter with 3 different height of pallet, and also compatible with backlight. If we need it, it's also possible. It means that we can have up to 2 square meter production for only 1.5 square meter footprint. All this is driven by our own softwares that we develop also by ourselves. But all this, perhaps it's more important, are modular. It means that we define with customer what they need, but above all, it is scalable. It means that if your needs change, we are able to upgrade the machine and add or remove some function. And a lot of function can be added at your factory. It's not useful to bring the machine back to our plant. So it can be really interesting, even if you need the stacker and you don't plan to use it first, you can add it by directly at yours. You don't need to the machine back to Laser Cheval. I would like to point out one innovation that I think it's perhaps really interesting for a lot of customers, because we don't need only this machine. We don't do only this machine to do mass production. We keep it very versatile. Even if you can produce large serial, you can also produce some prototype and small serial. And for this, we use a lot of different camera. I said that we can have up to 3 physical cameras, but we also can have a lot of virtual camera. For instance, in here you can see one camera with a picture of 22 by 14 millimeters with a focal length of 50 millimeters. It means that you can have a precision of 20 microns. And in the right-hand side, you have a smallest picture with, of course, a longer focal length and more precise. You can go down to 10 micrometer precision. We introduce a new possibility with our camera. It's what I call virtual camera. We can have stitched pictures. It means if you have big parts, or if you don't want to do specific toolings and you want to find the parts in a bigger area, you can use stitched pictures and do, for example, the localization directly on this picture, but the precision, of course, will be low, around 100 micrometers. But you can also do pre-visualization, pre-localization, and then when you find the part, you can go and use more precise camera and do the localization. So pre-localization and localization. It's really interesting if you have only some parts to do and you don't want to use a fixture, for example. So you can do fixture and use the stacker for large serial and just work on parts like this without any fixture and anything else. We go deeper. We use also another function. We can use some parts. We can search parts even if we don't know how many parts we have and where it is. It's just an example with coffee. If you don't know, if here you have a stitched picture, 70 by 50 millimeters. And even if you don't know how many parts you have to machine, the camera will find them and do what we have to do. All of this development make our machine the smallest in the market, less than 1.5 square meter footprint for more than 2 meter production. So it means that we put almost 50 years development for laser Cheval because we have 50 years old this year in the same machine, and we presented 2 weeks ago. So really happy to introduce this machine to you. And if you have any question, feel free to tell me, and or even you have my phone number and email if you need later on. Do not hesitate to contact me.
Thank you very much, Emric.
Welcome.
Do we have any question for Emric? I can perhaps have one regarding the materials that you can address with your machine. Do you mainly focus in metals? Do you also have glass capabilities,
Yes.
polymers perhaps?
Yes, of course, depending on which kind of laser source that you put in the machine. If you use a nanosecond laser, then it will be better on metal. If you use a femtosecond, yes, you can machine glass or sapphire or any other composite. If you want to weld parts, then you can put a QCW or CW laser and then weld some parts. So it's really a versatile machine.
Do you mainly work in the 1 micron region with the lasers? Do you also have you explored the 2 micron laser for certain applications?
Yes, we are working only in 1 micron laser. Yes, infrared. Yes.
Yeah. Very good.
Yeah.
So if there is no any other question for Emric, we are already a little bit late on the schedule. So thank you very much, Emric, for great presentation. And well, he already put all his details. You can also, as I mentioned, come back to me if you want to discuss with Emric or any of the other speakers. So thank you very much for being here today, and thank you to all our speakers. So Patrice, Scott, Olivier, Christian, Rüdiger, and Emric. Thank you very much for your nice presentations today. And well, I wish you a great afternoon. And in case your summer holidays are still in front of you, also good summer holidays. And we will be back with new events after summer holidays. So thank you and good afternoon.
Bye-bye.
Thanks a lot.
Thanks. Bye-bye.
Thanks. Bye-bye.
Bye, everybody.
Cheers, guys. Thanks again.
Thank you, Scott. Bye-bye.